So here I am back at the bench, and I'm poised now to make a double base bending iron on my standard wide cello shape. So this is the same as the wide cello iron, but instead of being 150mm deep, it's 250mm deep. Quite a big chunk of aluminium there. So I've already prepared this by with some magic marker on there, so I can see where my scribe lines are. So I'm going to just place the template on, and holding it firmly with my scriber, I'm going to mark out the outline. That done, and the template's still in place, I'm going to take my automatic centre punch, and on the template here are all the drillings. So we've got 4 mounting bolts, 3 heater holes, and 1 for a thermostat as well. So that's the mounting holes, 1 heater, 2 heaters, 3 heaters, 1 thermostat. That hole there isn't a hole to be drilled, that's where I hang the template up on the wall. Okay, so the next thing is to get that in the machine and start machining. So here we have the billet in the Henry Mills milling machine, and it's not in a vise, it's on some homemade vise ends. So at this side we've got a big block of steel fastened down by T-bolts, and at this end we've got two similar blocks of steel. One is fastened down by 2 T-bolts, but there's 2 clamping bolts in this one, which will then force this third block of steel up against the work, and then there's a locking nut on the top there on another T-bolt which holds it firmly down and stops it moving. And that supplies enough clamping force, but it means that I don't have the unnecessary height of and also possible chatter of a vise. It's firmly down on the table. It's raised off the table on 2 flat pieces of steel here, which I use to ensure that it is parallel to the bed. So once I've clamped it, I can feel if either of these are loose and make adjustments and square it off. You'll probably see that what I'll do in a minute is set up the camera on a stand, and I'll go through the mounting process and then set up the cutter. Okay, so we'll start with this top surface here. So I've got the fixed jaws down and fastened, so I'm just going to wind in the 2 clamping screws now. Get them as even as I can, so I want as much contact surface as possible. If the jaw is not parallel with the work, it's only touching in a very small area, and the holding force will not be very strong. Let's start putting it down and lock that jaw down to the table, and not surprisingly that one's come up a little. So we're down parallel now on the work. So let's get this shown on the road and select an appropriate speed. So as you can see, I've touched off the work there and begun cutting. This cutting is going to take some time as there's a lot of material to remove. This particular iron starts with a billet which is 6 inches or 150mm in diameter and 250mm long, and I removed possibly about 1/3 of that material in producing the shape. With the shorter irons being only 150mm in length, I can fit these in my metal cutting bandsaw and cut some of this portion off like this. I can then use some of these off-cut sections to make smaller bending irons and other things as direct With this larger bending iron, of course, I'm reduced to recycling the chips that come off this machine. As I don't make that many of these very large bending irons, this isn't really a problem just at the moment. Of course, if the quantity of these large bending irons were to increase going forwards, I would have to consider upgrading my metal cutting bandsaw. The machining process on such a large bending iron, of course, is rather time consuming and it will be very tedious to watch. So I'm doing quite a bit of very heavy-handed editing, as you can probably see. I will cover the whole process, but in a series of bites. Here we are on the final cut of the first flat of the bending iron. The first flat being, of course, the one that removes the majority of the material from the one side. The current cut, of course, is now down to the line scribed on the end of the bending iron, and the flat is forming a tangent with that curve. I'm now positioning the work in the fixture to start cutting the next flat. The work is repositioned after each flat meets the outline of the bending iron. And as you can see, the profile of the bending iron really starts to take shape. We're now approaching the completion of half the profile on this first side of the bending iron. The next thing we're going to do is move it over to complete the other half of this side's profile. You may have noticed that I'm not using any cutting lubricants or oils whilst I'm doing this process. That's because the cutter is tungsten carbide and cuts very freely without generating a lot of heat in the work. And to use oils and coolants would contaminate the chips and make them more difficult and problematic to recycle. Even though I'm using no coolants or lubricants, I'm able to cut up to 1/10 of an inch or 2.5 millimeters at one go on each cut. Once the rough profile is machined onto the one side, the work is then inverted and the process begins again on side 2. As before, the first cut is the deepest and the first flat takes the longest to get established. Of course, this is the process of making a large double base bending iron, but the processes for all my bending irons are essentially similar. All the processes are the same, they only vary in scale. And we're now very much on the home straight for this portion of the machining of the iron. So here we are, now we have the shape approximated by a series of parallel facets. Each facet, of course, being a tangent to the outline curve. Early on in the video, when I was marking out, you may remember I centre punched a series of holes for mounting bolts, heaters and for the thermostat. I'm now centre drilling those on the drill press. Before starting to record, I thought I'd framed this video pretty well and given you a good view, but I'd not considered my hand and arm in the operation of the drill press. I must apologise for that, I will improve in the future. I've now substituted the centre drill for a 5mm diameter twist drill, and I'm drilling the holes for the mounting bolts. You will notice that I'm using a little cutting lubricant on this. This is soluble oil and water. This helps to prevent the aluminium sticking to the twist drill, which it has a tendency to do. It also helps the drill run much cooler, particularly in the deeper holes for the heating elements. I'm now drilling the hole for the capillary bulb for the thermostat. This is also 5mm diameter on this model, and I'm using a long series drill because I want to get it nice and deep so that the bulb is actually positioned in the core of the iron to get a nice regular feedback for the thermostat. The eagle-eyed amongst you will have noticed that I don't have this workpiece in a vise or fixed down in any way. I would normally recommend that work is fixed down when drilling in a drill press, but in this particular instance there are certain advantages to not having it fixed down and very few risks associated with not having it fixed down. I don't want to take up a lot of time in this video explaining that right now, but if you're interested in knowing my reasonings behind this, perhaps leave me a comment and I'll see about making a video to explain further. So now I have a 10mm jobber's drill in the chuck and I'm beginning the process of boring the holes for the heaters. These are very deep holes. The heaters are 200mm long and I'm aiming to drill 220 to 230mm deep to position the heaters nicely in the core of the bending iron. So I'll start with a standard length drill and then I'll progress from there. With all three holes drilled with the standard drill, I've now switched to a long series drill, and this will allow me to take these holes down to around about 150mm deep. Incidentally, this is the drill that I use for doing my standard length bending irons, the 150mm bending irons, and I drill generally to around 120-130mm deep for those. By this point in the filming I'd realised what was going on with the camera angle and repositioned the camera so that you get a better view. Obviously this is quite time consuming to drill these really long holes, and it's important to keep the holes clear of swarf as much as possible. Even with long helix drills like this, the chips no longer self-eject, and it's important to keep stopping and clearing the work from chips. I'm using a special drill now, an extra long series drill, which is really long. It actually is 300mm long, but that allows me to get to the depth I want for these holes, for these heaters. The deeper I go, the slower progress is, because I have to spend more time clearing the swarf and reapplying the coolant. Eventually though, all three holes are to depth and we're ready to begin the next process. The next job is to tap the holes for the mounting bolts. I'm using a helical flute machine tap in a battery drill with a little cutting lubricant because it's just an efficient and quick way of making these threads far quicker than using a hand tap. So once all the holes are drilled and tapped, I use the mounting holes, the threaded holes, to fasten it onto a piece of stock, which I can put in my vise then, and I got full access to the work. So my initial cleaning up, I use this device, which is actually designed for cleaning and polishing pipes, cleaning welds off pipes, and it's got an abrasive belt and it's sprung loaded, so it conforms to the shape or the curve of what's being cleaned.
I begin this process with an 80 grit belt. This quite quickly removes the high spots where each of the facets meet. This is actually very useful because it gives me some parallel lines to work to, and with careful observation I can ensure that the shape and the consistency of the iron is not compromised by this process. I then moved to a 120 grit belt for further cleaning and added accuracy and sort of smoother finish. Then finally on to a 240 grit belt. Once I'm happy with the shape and the work I've done with the belt linisher, I progress on to some handwork. This usually begins with me hand filing a chamfer on the top of the iron. Once I'm happy with this, I progress to cleaning up by hand with abrasives. Initially with the chamfer, then with the top surface, then around the rest of the profile of the iron. I use various processes for this, as you can see with a sanding block, but also stropping or strapping and other various hand processes. The time that this gives me allows me to sort of look at the profile of the iron and to clear up any little blemishes and other inaccuracies that might have occurred during the machining process or during the belt linishing. Once I'm entirely happy with the profile and the finish of the iron, I'll take it to the sandblaster, where it will be blasted with spherical glass beads, which imparts a nice even matte finish to the finished article. I fabricate the base boxes myself from aluminium and TIG weld them together. I've made them in advance, so I can't show you the production of this box. I'm cleaning it up with a flap wheel on an angle grinder. I may make the production of these boxes the subject of a future video if there's some interest. I used to work through different grades of flap wheel on the angle grinder to finish these boxes, but nowadays I also sandblast them so that their finish matches the iron. Next is marking out for the mounting of the bending iron and also all the ancillary components. Having marked the centre, I used the bending iron template to mark all the holes commensurate with mounting the bending iron. Next, I mark the position of the thermostat and also the indicating neon. Lastly, marking on the back of the bending iron, I'm going to mark up for the gland for the flex, and also on this particular bending iron I'm fitting a fuse holder because it's going to be used in the EU with an EU plug which doesn't have a fuse. All those holes have now been drilled to appropriate sizes. The next job is to deburr them and then to finally finish the box and sandblast it. Meanwhile, I need to prepare a piece of insulation which fits between the bending iron and the base box. I use the same template for this and mark out the outline and also the holes. This insulation is asbestos-free fibre cement board called Superlux. Once all the holes are drilled and the outline cut out by the bandsaw, I have to clean up the edges and tidy it generally with a hand file. Now we're in a position for where final assembly can begin. This starts with the insertion of the heaters. Then the positioning of the insulation. Followed by the base box, of course. The base box and bending iron are fastened together using M6 bolts incorporating anti-shake star washers. I like to leave the torque clutch on my power driver relatively loose to avoid any potential damage and tighten up all screws by hand finally. Looking good. Here I'm inserting the indicator neon which simply clips into the 10mm hole. The next job is to position the analog thermostat and then to insert the capillary bulb into the deep hole already drilled in the bending iron. Then I fit the flex gland. This not only provides ingress protection for dust and moisture, but also provides strain relief on the flex. As I mentioned before, I'm also fitting a fuse holder to this bending iron, so that's the next job. I always fit my irons with braided flex. Not only is it abrasion resistant, it's also resistant to heat should it accidentally come in contact with the iron at any time. Before cutting the outer insulation off the flex, I like to wrap it in tape so that it prevents the fraying of the braided outer casing. With the flex firmly fitted into the gland, I can progress with the inner connections. I generally start with the earth or ground connection first, fitting a crimped eye and then fastening it to one of the mounting bolts of the thermostat. Once the thermostat is firmly attached, I attach the operating knob to it and test its operation. Here I'm taking the incoming live conductor and preparing it to attach to the fuse holder. Here I'm taking one conductor from each of the 3 heaters and connecting it via a crimp to 2 other conductors, one to connect to the thermostat and the other to connect to one of the terminals on the indicator neon. I'm now soldering the incoming live conductor to the fuse holder. I'm now taking the 3 remaining conductors from the heaters and coupling them together via a crimp to the incoming neutral conductor and a connector for the other terminal of the indicating neon. The last remaining connection to make is between the fuse holder and the input of the thermostat. With all the internal connections made, of course, now we have to fit the power plug. As before, I tape the flex to prevent any fraying from the braided cable. Firstly, I tighten up the strain relief clamp on the flex, and then I go on to fit the first conductor, which in this case is the earth or ground. After then fitting the live and neutral conductors to their respective pins, I reassemble the plug. It's then time for some testing, which begins with earth or ground continuity between the earth pin of the plug and extraneous metal components of the unit. The next test is insulation resistance testing, or earth leakage it's sometimes called, and this tests between the live and neutral connectors and the earth. You may have spotted me just turn the thermostat on just then. It's important that the heaters are live for this test, and we're getting greater than 999 megaohms. Next is functional testing, so time to power it up. I start with it on a low temperature, and I like to have a feel at it as it starts to warm up to ensure that it's warming up evenly and that all the heaters are working properly as they should and that heat is being transmitted through the iron as it should be. I then increase the temperature to 100, then 150, then 200, then 250, and leave it on for a little while and ensure that the thermostat is cutting in and out as it should do. Once these functional tests are complete, I bring out the meter and test both earth continuity and insulation resistance again whilst the iron's still hot. So the appliance passes the test again even whilst hot, with a minuscule earth resistance and massive over 999 megaohm resistance on insulation. Just to put this into context, in the UK for portable appliance, or PAT testing as it's called, the minimum requirement is 2 megohms. The next thing to do is to fit the baseboard to the iron. I would normally do this before running the tests actually. I will run the tests again after this is fitted to ensure that nothing's been pinched by any bolts. The baseboard is 18mm birch ply, and it's been applied with a layer of Danish oil, and it's secured with M6 bolts. Again, I like to always do the final tightening by hand so I know how tight everything is. Only once everything is complete and all the tests passed do I apply labels. Then a quick clean to remove any dust and fingerprints. I mark each bending iron with a unique serial number. That's because I record all the details of the components and the sizes and specifications for each bending iron. So if there are any problems, any breakdowns, or if any spare parts are required, I have all the data I need. If you have any questions about anything you've seen in this video, or if you want to know more about my bending irons or other tools I make, or if you have any ideas or requests for future videos, please leave a comment below. I plan to make more videos about my tools, my workshop practices, as well as guitar making and repairing, so if any of this is of interest to you, please like and subscribe. Do check out my other videos and my website too, caramillo.co.uk.